Hello, everyone. Welcome to this particular talk. And my name is Santanu Das, and with me I have Debasish Das. He's also a co-author of this particular work. And we are actually from Verizon's lab, and we are located in Palo Alto. So before I jump into the slides, one point I'll try to make here is the contribution we are making here is more towards the MLlib, and more specifically, it's towards the recommendation system. But while doing the work, we realized like this kind of contribution we just made can actually open up other avenues, like in terms of classification and detection. So what to expect from this talk? Primarily, we'll be talking a little bit about like what essentially matrix factorization is, and then more specifically, we will focus on the formulation for the non-negative matrix factorization. And in that context, we'll actually introduce two different kinds of algorithm to solve a particular quadratic minimization problem. Followed by that, we'll actually go through a few use cases, like we'll actually demonstrate the different constraints. Particularly, the interesting ones are the linear constraints, where we'll show sparsity bounds and equality constraints. And we'll actually end up the talk with some results and discussion. And at the end, we'll actually go with the QA. So from matrix factorization point of view, what essentially it means, suppose we have a rating matrix. What we essentially want to do is to get two metrics out of it. We want to decompose it in terms of two matrices. One of them is basically a user factor matrix. The other one is movie factor matrix in this case. And the equation we are seeing in this slide is a very generic one, where the first term is showing like we want to decompose the rating matrix in terms of the two factor matrices such that the reconstruction error is minimized. And at the same time, the second and the third term is fundamentally introducing sparsity on those two particular factor matrices. And the third term and the fifth term is essentially introducing some sort of smoothing factor. So this is the current state of the art in Spark right now. So it's basically the alternating least square method. In this particular technique, what we do is we fix one of the factor matrices at one time and then estimate the other one. And in that case, in that way, we actually repeat the whole method until convergence. What I want to point out here is, in the current Spark implementation, there are two different loops, the inner loop and the outer loop. In the inner loop, what we do is we basically get a tolerance-based solution, and in the outer loop, we actually repeat the same method until convergence. And the reason why I'm mentioning this is our contribution is more towards the inner loop, where we will show how to introduce more capability and advance the current state of the art. So we already know, like, non-negative matrix factorization is essentially clustering. So what we are doing here is we are solving an independent problem, and that's given by the equation below. And once we get those individual solutions, which is H1, H2 till Hn, we actually get the aggregated solution. And again, once again, our contribution here is introducing a quadratic programming solver, which is more in the inner loop side. We are still using the outer loop the way it has been implemented in Spark. So here we are introducing two different algorithms. One is ADMM, which is alternating direction method of multipliers, and the second one is SOCP, which is basically second order conic problem. And so what what ADMM does is basically it's a divide and conquer kind of technique where it decomposes a complicated problem into smaller sub-problem and finds out an effective way of solving it. And at the same time, at the end, it kinds of try to achieve some sort of consensus. That's a very high-level description of ADMM. And for ECOS, which is actually is an acronym of Embedded Conic Solver. So what it does, it solves like specific class of problems that can be expressed or formulated in terms of SOCP, and ultimately it will be solved using interior point method. So we actually did some very preliminary experiments, and what we saw is, in some cases, ADMM performs better, where the constraints are much simpler, but ECOS actually can handle very complicated kind of constraints. But again, I want to emphasize that these test scenarios will have to do more investigations in future. So from now onwards, I'm going to hand over the slides to Debasish, and he will run you through the rest of the presentation.
Thanks a lot, Santanu. So the first one is the quadratic programming formulation written as ADMM. So we know that the objective function, as you can see, is a standard quadratic programming. But in this, we are trying to take the constraint. So in this particular slide, I am giving a very simple constraint, which is just positivity. And we are trying to make an ADMM formulation, which is the standard consensus formulation out of it. And you can see that there are 3 steps. One is your step to optimize H, and then the ZK. And the third step is the dual variable. So these are the standard steps. So you can look into the ADMM reference from Professor Boyd, and you can see these in action. This is how it looks like when you write it in Spark. So all you have to give it is that in your solve API, you give your gram matrix, and then you give your linear objective part. And after that, if your problem have equality, you specify that. If not, you don't have to. And then the standard solve, we do a direct solve right now. So we do a Cholesky, and after that, there is an ADMM loop. So the second slide shows you how does that ADMM loop looks like. I think the key point in this that which comes of Scala and Spark and the flexibility that we get. So it's this solve triangular is basically a triangular solver, which is called from BLAS. And thanks to Scala and then Breeze and Spark, we are calling the native Fortran code to get this triangular solve. So you get native runtime. And the third step, like the proximal step that you see is basically the second ADMM step, which takes your Z and puts it to a valid place where your constraints are satisfied. And then it's a very simple algorithm, and you loop till your X, Z, and U variable converges. Now, why did we have a SOCP formulation still? Because with this project, we are trying to bring the most standard constraint solver that is possible to Spark, and which means this will open up avenues to solve linear problems with linear constraints, quadratic problem with linear constraints, and you can also solve linear problem or quadratic problems with quadratic constraints. So this is SOCP formulation shows that how do we take a quadratic problem and translate it into a SOCP formulation. So what we do is we transform the problem into a quadratic constraint, and the main trick is that we do a Cholesky transformation in a way that the Cholesky factor transpose Cholesky factor will give us back this quadratic constraint, and then we take a square root of that and we get back the quadratic constraint represented as a linear constraint. And this is the latest, I think, SOCP most likely is the most efficient linear solvers that is possible right now. So we did this to see that which problems need SOCP solver. Like if our problem has a very difficult constraint, we wanted to see how does the SOCP solver behaves as compared to the ADMM version. Now in this code, you can see how do we implement a very basic SOCP solve. So in this, the API is a bit more complicated because you make your QP solver with how many gram matrix, what's the size of your gram matrix, and also by this, we make use of the Breeze compressed sparse matrix. So by this, you specify the structure of the equality constraints. The second one, you specify the structure of your inequalities. So this is like the complete formulation. So you can solve any problem, linearly constrained problem that you can. And after that, thanks to, again, Spark and Scala, so we are calling a native library, which is written in C. Now, why we are calling a native library in C is because to solve this, we need a sparse linear algebra. And right now on the JVM, there are no sparse linear algebra. So what we did was that there's Professor Tim Davis has his code, which we wrapped it up, and we call it through a native library. And we have not seen a very big runtime loss going from Scala to Java to native, very less runtime loss. So this is one way. Now I will show you some of the use cases of applying these. So first use case is that what if we have some positivity? So what we want is that all the factors should be positive. So this is very common for cases where you are doing feature extraction from photographs. So where you can't have your factors with negative numbers. So in the test, we are just showing some very basic proof of concept test that how different is the result from the octave. And we have found out is that almost all of them give you very similar answer, except that we got some purity, like more pure results with the ECOS and ADMM. This shows you the Spark code. So that's how we put it inside Spark MLlib recommendation. So the structure, if you are familiar with Spark code base, then you will see that there's minimal change. So all we are doing is that for H and F matrix, we have to derive them, and we send them to the QP solver, and we solve it. Now this shows you what is the projection operator, which is the Z update. So you have to take the Z values, which came out of your ADMM algorithm, and you have to project it to a box, which means lower bound is 0, upper bound is say 1 or 10. So you have to project it to that box, and this shows you how simple the code is to take and project the Z value into lower and upper bounds. The second use case is sparsity, which is L1 regularization. We don't have it in Spark yet, so this will be our major contribution. So in this, I'm just showing that where does the sparsity show up. So in some cases where we know the signal from which the problem came is a sparse signal, so we need to generate factors which are sparse. So that's one of our motivations to do this. And this is, again, some basic test to see that when we solve this problem with some, I think for this problem, we put a regularization of 2. And this is a 25 factor. So the total latent factor we are finding is 25. And we are just trying to see that, is it true that how close are we to the octave? And we have found. So this is in alternating least square that Spark has. We cannot solve this. But what we have found is that our ECOS and DMM solvers both give you sparse answers. Now, this is again, how do we write this code in MLlib? So the ways to do is that you make a new direct solver and you set that the proximal, what proximal operator do you want to make use of? In this case, it is an L1. And then we just put a lambda on this. So, and then you do the solve. Now, this is the proximal operator for L1 solve. So this comes from a paper from Rockefeller. Later, it has been used in ADMM papers. So this is called soft thresholding. So the code is very simple for this too. Now, the third use case, which is a bit more complicated, because in this we are not only doing, so we want to force a bound constraint on each of the factor, which says that each of the factor in your matrix factorization should be between 0 or 0, 1. But with that, we also want to force the summation of all the factors should be equal to C. In this case, we took C as 1. And then we just did some basic tests to see that if our result matches with Octave or not. So in this, again, ALS cannot solve this, but our results, both of them, ECOS and DMM based, were very close to Octave. Now, this is again, is a bit more difficult because you have to specify the structure of your equality constraint. So the first one, you build a compressed sparse matrix, which shows you what kind of equality you want to force. And then you put a bound constraint. And then you make your QP solver. And after that, the solve technique is same. So you put this code into Spark, and then you just put the gram matrix part, the linear objective part, and you solve it. Now, in this slide, finally, I want to show you some of the runtime experiments we did. We took a movie lens data set, which comes with MLlib now, which has 1M ratings from 6,000 subscriber, 3,000 movies. Now, you see, the way to run the code is not very different than what you do right now. I did local testing just because I wanted to see how far are we in terms of runtime compared to the least square, which is the basic, the baseline. So the way to specify what kind of QP problem you want to solve is just an option. So we have right now 5 different versions of the problem that we can solve. So these 5 different versions are the basic quadratic minimization, which is least square. Then you can put positivity, so each factor should be larger than 0. Then you can put bounds, which means each factor should be between 0 and 10, say. Then you can put sparsity, that each factor, each out of the 25 latent factor you want, it should be within like only 4 factors you want to pick. And the third one is equality and bounds. So, in the runtime, the basic result is that for QP and QP with positive QP and bounds, our DMM-based algorithm was at par with least square or slow, a bit slower than that, but we are much faster than ECOS-based interior point method. So what it says that if the constraints are simple, like QP or QP with bounds or QP with L1, then ADMM-based algorithm works really well. But on our QP equality, we found that SOCP solver or a interior point-based solver was giving us better runtime. So we are still trying to look into that. So our main goal is that if we can bridge the runtime and make it ADMM to make it as faster as ECOS. Now, future work, we want to put this inside Spark So there has to be a lot of testing being done since a lot of new options will come in with this change. Also, the runtime optimizations that I showed, so we have to look into that. So what our main goal is that we should not be much slower than the baseline least square. But of course, we are solving much complicated problems. But still, we want to optimize as much as we can. We also want to look into the matrix factorization case where like the values are not considered missing, so that needs a gram matrix broadcast. I think last day we had a talk on this. We want to see how on our large scale data sets, how does it scale, or do we need to do more changes? Now, the fourth one, I still need to talk with the community that does the community need a linear programming or a SOCP solver? So we do have the code. If the community needs, we can expose it. The fifth one is so all the solvers we wrote so far, they make a Cholesky factorization. So when your ranks are large, which is if you want to do a kernel version of support vectors, so your ranks can be pretty large. So for those, we want to come up with an iterative version of these solvers. And of course, we are going to do a lot of applications of these solvers to our data sets. And hopefully next, we will going to show a lot of these things in upcoming days. So from here, I can take questions. Yeah.
So it was not clear like how you utilized Spark here, because like I think the size you just have gram matrix.
Yeah.
So you really did not need to use any distributed Spark here, because like I don't see any distributed step in the derivations of the EDMM.
Oh no, DMM is not distributed. So if you look at the Spark code base in MLlib recommendation, you will see a step like this. So that step, right? So matrix factorization problem, Spark distributes it to a way that every solve becomes a data local. Now our solver comes after that. Yes, so X transpose X comes from Spark, then we send it to our solver, get the answer back. Yeah. Sure.
So after 1.0, we put non-active list sparse solver into ARS. That's based on projected conjugate gradient.
Yeah.
So did you run some experiments
Yes.
against that? What's the
So right now that's your QP positive. So right now, the DMM version is around 6x slower as compared to that. So we are still looking into that, why is this? Since our version of the code uses direct Cholesky factorization, while that version of the code does a conjugate gradient. So we are still looking into that. If we move our solver to the CG version, we should get back to the same kind of runtime.
What's the size of K here for this experiment?
25, you mean the rank?
Yes.
Yeah, the rank is 25 or this. And we will scale it more, yeah.
Second question is, basically, if you want to promote sparsity, you don't need to put an L1 constraint. If you put a non-active constraint, it's already promote sparsity. So
Yes.
compare the sparsity from the result between the positive constraint and L1 constraint.
We found very different answers, yeah. So since L1, when we put L1, we don't put positivity because that does not make sense, right? But we have found in our runs is that the X, like the L1 and positivity were giving different results, but I don't know how does that translate to the recommendation and the whole rest of the flow. So we have not done that experiment yet, but yeah, we will be doing that. So I think in literature, there has been a lot of work on sparse NMF. So we wanted to keep those features. Like if someone wants to make use of L1, he should be able to. Yes, yes. So we want to put the code back in. So we are still talking with our like legal and all, but the plan is to put the code back in. Yes. Yeah. I saw some else. Okay. Yeah.
Can I ask the size of the data that you used out here? Like,
So
do you have any time evaluation for time analysis for the data that you have used?
yeah. So this one, right? So that's the movie lens. That's the data set we made use of. This. Yes, but this problem was too small, so we did not want to like see our large-scale data sets on it yet. So this was more like a standalone testing to see how far are we in terms of speed, since we want to be as fast as least square. So this testing is trying to move us to that place, and once we have this thing runs on distributed. We have tested that, but since we wanted to focus on the runtime of each local solve, so that's why I am not showing data on that.
And in the distributed one, would you say like this algorithm performs similar to what they have for the?
Yeah, since it all scales, right? Since the Spark ALS will scale based on the number of cores you give. Yeah. Okay. Thanks a lot.